The intention of this lab was to use the motion and path of an orbiting star as well as its mass to determine the mass of a black hole about which it is orbiting. This was visualized and calculated by using a computational model through GlowScript as well as physics principles including the momentum principle and Newton's second law. These concepts were able to contribute to the calculation of the mass of this black hole. Another principle that was necessary in the understanding of the motion of the star was the parallel and perpendicular components of the forces acting on the star coming from the black hole. In a similar way, it was important to understand the calculations of the parallel and perpendicular components of the momentum of the star in centripetal motion. These physics concepts and formulas utilize the path of the star as well as its mass and distance from the black hole at different times. The momentum principle was crucial to the calculation of the mass of the black hole, since it allows for the assumption that change in momentum is equal to F net, which is necessary in calculating the mass of the black hole, as you will see later on. Another key understanding of force and momentum in this situation is that F net as well as momentum are the combinations of their parallel and perpendicular components. In the case of this orbiting star, the perpendicular force was perpendicular to the velocity of the star and points inwards towards the black hole. The path of the star was not uniform. However, if a kissing circle was created at each instance of motion, then the perpendicular component of the force would be pointed inwards toward the center of the circle. However, the parallel force is parallel to the velocity of the star and in the same direction. Newton's law of universal gravitation was also used when finding the mass of the black hole from the force that the black hole exerts on the star. Rearranging this equation uses the mass of the star, distance in the black hole, and calculated net force at each point to find the mass of the black hole. All of these concepts come into play in the development of a program to model the motion of the star around the black hole. I used the program GlowScript to model the trajectory of the star and began by inputting my email address as a seed for the black hole to create a unique mass. Additionally, I inputted the mass of the star, which is 2.0 times 10 to the 30th kilograms, as well as delta T, which is equal to the amount of seconds in one day, being 86,400 seconds. The other significant part of this program was a while loop that iterates through the motion of the star and calculates the mass of the black hole during each iteration. In this section of the code, I set the initial momentum to the mass x and to the mass times the initial velocity using the momentum formula P equals mv. For the final momentum, I used the same formula with final velocity. These values were used to calculate change in momentum and the change in velocity during this time. dp dt was calculated by dividing the change in momentum by the change in time, and using the momentum principle, it was set equal to F net as well. From this, the perpendicular and parallel momentum were calculated in the next section. Finally, the mass of the black hole was calculated by rearranging the formula for gravitational force. I changed the equation to be equal to the mass of the black hole and used values from the magnitude of F net, the mass of the star, and magnitude of the distance between the star and the black hole to produce the mass of the black hole during each iteration. This value changed slightly each time because F net changed with the variation in change of momentum during each interval, but produced a value consistently around 9.18 times 10 to the 33rd kilograms. Here is a model of this program. Let's talk about how the force and the momentum components differ from one another. The force is initiating the change in momentum, since acceleration changes velocity, which is necessary in changing momentum. For this reason, while they have the same numerical values, they are referencing different things. It is also important to note that the rate of change of momentum is equal to the resultant force and doesn't necessarily mean that the components of the values are equal. What if the black hole was replaced with a black hole of a different mass, but the motion of the star remained the same? In this case, we would not be able to determine the mass of the black hole because the change in velocity and the distance between the star and black hole would not be reflective of the force of the black hole and the star. These values are essential in finding the mass of the black hole, so changing them would be necessary in finding the new value of the mass of a new black hole.